Section 9.5a is about factoring a difference of squares. A difference of squares is a special kind of polynomial that you have, and we're going to teach you a pattern that can allow you to factor it very simply. A difference of squares looks like this. It has a perfect square in the front, a perfect square in the back, and a minus sign in the middle. If you ever have a polynomial that fits that criteria, you can use the pattern that you're about to see here. Now, one of the things about a perfect square or a difference of squares is it involves numbers like the number 9, which is a perfect square. I'm going to list for you a large group of perfect squares, starting with the number 1. The number 1 is a perfect square because it's created from 1 squared. And I'm going to list all the numbers up to 15. So here you see a large list of perfect squares. These numbers that you see here in orange, they are the perfect squares because they're created by squaring some other number. And those numbers are things that you want to look for whenever you see a difference of squares. Now, once you know that you have what's called a difference of squares, once you know that you have something squared with a minus sign and then something else squared, this is the pattern you're going to use. You take whatever creates the square in the first term and put it in the first group of parentheses and the second. You take whatever creates the square in the second term, put that at the end of each one, and you put a plus sign in the first binomial and a minus sign in the second binomial. That's the pattern that we're going to use. Let's take a look at an example. This is a difference of squares because n squared is a perfect square and so is 25. So the question we ask ourselves is, what squared gives you n squared? The answer is n times n. Also ask ourselves, what squared gives you 25? Well, if you look back at the list here, 5 squared gives us 25. So we put a 5 in the first one and the second one. We make one of these binomials a plus and one a minus. And that is how you factor a difference of squares. Let's go to this one. Is it a difference of squares? Sure it is. 36 is a perfect square, so is x squared, 49, and y squared. What gives us 36? 6 and 6. What squared gives you x squared? X and x. 49 y squared comes from a 7y times a 7y. One of them is a plus and the other is a minus. Here's an example we're told to factor, but if you look at it, 48 is not a perfect square. Neither is a cubed, neither is 12, and there's nothing here that's a perfect square. So we can't use our difference of squares idea. But we can still factor. We go back to the first kind of factoring that we learned, which was taking out a GCF. And it looks to me like the number 12 and the letter A is the greatest common factor here. Well, when I take 12 out of 48, I'm left with a 4 because 12 times 4 is 48. I'm also left with an a squared minus a 1. Now, in previous videos, we've stopped right there. But if you look now inside these parentheses, 4a squared is a perfect square. So is 1, and there's a minus sign. So that's a difference of squares, which we now know how to factor using our pattern. 4a squared comes from a 2a and a 2a, and 1 comes from a 1 times 1. Put a plus sign and a minus sign. And here's an example of one where we had to factor 2 times. First time using a GCF, second time using this difference of squares idea. Here's an example, has 2 terms, so we might want to think difference of squares because there's a minus sign in the middle, except 2 is not a perfect square, neither is 162. I would like to point out, though, that x to the 4th is a perfect square. I want you to write this down because it's an important point we haven't talked about yet. Any even exponent is a perfect square. So if you ever have a letter to an odd exponent, you know it's not a perfect square. If it's an even exponent, you know it is a perfect square. And the reason is because if you take anything like a to the 3rd and square it, you get a to the 6th. If you take something like x to the 4th and square it, you get x to the 8th. Anytime you have an even exponent, you can cut it in half and turn it into the monomial that would be squared. So that's kind of a side note that you need to know about exponents. But back to our original problem here, this is not a difference of squares, but it does have a GCF. I'm going to take a 2 out, and I'm going to get an 81. Now what's left has a minus sign. X to the 4th is a perfect square. We just talked about that. And 81 is a perfect square, so this is a difference of squares. Now what squared gives me x to the 4th? X squared times x squared. And then 9 times 9 is 81. One's got a plus sign, one's got a minus sign. Now perhaps you'll notice this. we actually created another difference of squares. X squared is a perfect square, and so is 9. So we write the rest of it out, and then we factor this difference of squares with an x and an x, and 3 times 3 is 9. One's got a plus, one's got a minus. So there's a bunch of different ways to factor this one, and eventually you all get down to this line. Here's an example that you might be asking, why is it even in this section? Because it doesn't have a difference of squares. Well, you'd be right, but eventually as we simplify we will get to a difference of squares. But we'll start by taking out a GCF of 5. And now what we're left with is a 4-term polynomial that we're supposed to group, because that's how we factor 4 terms. We take out an x squared here, left with an x plus 3, and then take out a negative 1 in the second group, left with an x plus 3. So we have x plus 3 times what's left, x squared minus 1. Now don't forget this 5 that we factored out is still part of the factors, and it has to be included. But now you might look at this and notice, well, here's the difference of squares that we were looking for. How do you factor x squared minus 1? We use x plus 1 and x minus 1.